Right. See, when it comes to history of periodic table, the first thing we need to know is that in the early centuries, it was the Lavoisier classification, which was the first of a kind, where we try to figure out that there are different elements present. Now, these are categorized into two different forms, metals and non-metals. Okay. Whenever there is a tendency of losing electrons from the atom, we designated them as metals, and the tendency to gain the electrons, we designated them as non-metals. Okay. For instance, uh, if you compare elements like sodium, potassium, calcium, gold, silver, aluminum, these were all categorized as metals. Why? Since they are metals, we expect them to lose the electrons and converts into positive ions. We expect them to convert into positive ions like this. Okay. This is what is expected out of the elements. Okay. Next. While when it comes to non-metals, right, so that includes iodine, bromine, chlorine, sulfur, carbon, phosphorus, these ones. These were non-metals. And usually when it comes to non-metals, for example, if you take Br, okay, Br has the ability to accept an electron and convert itself into a negatively charged species. Now remember that any element which is positively charged species, we call it as a cation. And any element which has negative charge on it, we call it as anion. So it is an cationic species and anionic species. So this was first of a kind to, kind of categorize the elements. Next, the second of a kind is Prout's hypothesis, right? Where every element is expected to be made out of hydrogen atoms. And if the atomic weight of hydrogen is 1, every other element is expected to be just the integral value of hydrogen. For example, carbon was considered as 6 times of weight of hydrogen. Oxygen was considered as 8 times of weight of hydrogen. Okay. So this is also a very simple categorization, but not a very worthy discovery or anything here. Got it? Next comes the de Brognie's triads. Correct? Around 1817, he was able to identify elements in the form of sets. Okay. So he found the set of three elements which all show similar chemical properties. He called them as triads. Okay. Atomic mass of the central atom will be average of the first and last, which is pretty much matching for a lot of the cases. Correct? For example, if you take chlorine, bromine, and iodine, chlorine's atomic mass was average around 35.5 gram per mole, or simply 35.5 mass number. You call it as mass number. Okay. Iodine was 127. The average was exactly coming out to be 81.2, but nearly very, very close value was there for bromine, because bromine's actual atomic mass is 80. So that's not a bad averaging. It was very close to it. Similarly, if you take calcium, strontium, and barium, it was found that calcium was 40, barium is 137 mass number, chromium is averaging out, comes out to be around 88.5, but the exact value of strontium was 87.6. Okay, so which is also not bad. It is pretty much close value here also. Okay, likewise, if you notice lithium, sodium, and potassium, lithium's mass number was 7, potassium mass number is 19. Now, this time when it comes to sodium, 23 was a very good match. So, these are those triads. That means chlorine, bromine, and iodine are expected to have a similar property. Same is the case with calcium, strontium, barium. Then same is the case with lithium, sodium, and potassium. Okay. So few other triads which almost gave a very good result includes potassium, rubidium, cesium. These three as one triad. Phosphorus, arsenic, antimony, sulfur, selenium, tellurium. Okay. Hydrogen, fluorine, and chlorine. Very interesting one. Hydrogen, fluorine, and chlorine. And scandium, yttrium, and lanthanum. Okay. Clear. One more was iron, cobalt, nickel. Got it? These were the triads which are mostly observed, to almost a good averaging of the center element. Got it? This is one standard JEE question. Nowadays they are not asking, but earlier they always used to ask which of the following is a correct set of Doberineer triads. So these are the sets which you need to remember. Okay? Everybody clear on that? The people who has the class note, the pre-notes can start writing simultaneously with me. Others wait and just learn what we are doing. Later, take the printout. Okay. Clear with this part, everybody?
Yes.
Danish with me, Vita? Right. Good.
So can you just give me 1 second to write it?
Yeah, sure. Next. Check what was Newland's octaves. As per his theory, what he noticed that every eighth element in a particular sequence will always have a repeated property of the first element, while we have to arrange those eight elements in the increasing order of the atomic mass. Okay. They always mimic with the Hindustani or classical or Carnatic music, right? Just like how we have sare gama pada nisa. Correct. So that is, if you have sa, re, ga, ma, pa, da, ni. Again, the sa will be repeated. Correct. What has been noticed is that lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, potassium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, and calcium. Up to these elements were perfectly fit. Okay. And it also explains the fact that lithium, sodium, potassium have very similar properties. Same goes with beryllium, potassium, when it comes to, sorry, this is magnesium, beryllium, magnesium, and calcium, and boron and aluminum, carbon and silicon, and so on. But the problem came after calcium. After calcium, this property was not so very well recognized, or it wasn't followed the way it was thought so. So that means it's a good way of observing the elements and their properties. But the drawback is it is only valid up to calcium. No inert gas are included, no hydrogen is included, no D block elements. That means heavy metals were not included into this list. Got it? So this was about Newland's octaves. Clear, everybody? Very simple case here, right? Next. This is pretty important. Lothar-Meyer curve. So far, the first four were most of a proposals without any evidence. But Lothar-Meyer curve was the first kind which was with evidence. What he did, he took the data of atomic volume and he plotted the data with its atomic mass. As many elements it was known, he tried to figure out its atomic volume and try to check how the atomic mass is. And as the increasing atomic mass you have, he tried to plot as many elements as possible. All right. Then he noticed a very, very nice pattern here. Okay. What is the first pattern notice is that most of these elements, rubidium, potassium, sodium, and lithium, they were actually always be on the peaks of the respective curves. Got it? And these were designated as most electropositive elements. That means their ability to give away electron is very high. Okay. Next, slightly lesser electropositive elements were sliding down that peak. Okay. So sliding down this peak, you will see you'll have next most electronegative elements, including beryllium, magnesium, calcium, strontium, and even as you go towards this side, it will be barium. Okay. So it is observed as you descend the peaks. Next, halogens were observed while ascending the peaks. So that is, if you notice, fluorine, chlorine, bromine, and then comes iodine, and so on. This is the way it was rising up. Okay, go get your water. Next, metalloids like silicon, arsenic, antimony, tellurium, they all were identified to occupy at the bottom of the curve. Got it? Like this here, you can see at this bottom of the curve, somewhere here, 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 like this here, they were mostly found at these positions. Okay, and another thing, most of the D block elements, right from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, they all were found at a very, very close space. They all were identified to be very, very close space. Okay, so I'll write down that scandium towards nickel. So there was a nice pattern that was observed here, correct? And he proposed that the periodic properties of these elements are the periodic functions of their atomic weights. That means as the atomic weight changes, their property will also change. That was the main proposal that was given by Lothar Meyer curves. Got it? Which is to certain extent actually right, correct? Because most of these elements, as their mass is increasing, their properties are changing. Correct? So the next one, this was the main observation, but the main drawback of Lothar Meyer curve was he could not identify the right data for all the elements. That is, how much is the exact atomic volume versus its exact atomic mass. So identifying data was a bigger challenge for Lothar Meyer curves. Second problem is that there is no simple pattern to remember. It was a very complex pattern because it was mainly dependent on the graph. So it was very difficult to, it's very difficult to remember or recall that. Okay. Third biggest challenge was when it comes to inert gases, hydrogen, and even up to carbon, these properties will not very well matching. That is, when you have a lower atomic weights or when you have inert gases, they were not perfectly fitting into these curves. Okay, so these are few challenges of Lothar Meyer curves. But the basic idea behind the Lothar Meyer curve. At what time? Sorry, check. The next one was about Mendeleev's periodic table. Now, he took all the good information from Lothar Meyer curves and he proposed the same thing, that the physical and chemical properties of elements or the periodic functions of their atomic weights, same as Lothar Meyer curves. Got it? Then, instead of simply using a curve, he came up with a new idea that why don't we put it like a table and make 7 rows and 8 columns. So he made 7 rows and 8 columns. And in that matrix of boxes, he was able to fit 63 elements. out of which inert gas was still not perfectly fitting. They were unknown at that time. He left some boxes that way, considering that these are the elements which haven't been discovered yet. Okay. Then he arranged them in a vertical and horizontal rows and columns. There are 7 rows, which we call it as periods. There are 8 columns, which we call it as groups. Going ahead, we'll be using this term a lot of times, groups and periods. And notice each group had A and B subgroup. That means within the box, you made it into 2 compartments. One is A and the other one is B. These are subgroups. Okay. The elements in A are normal elements. That means in the sequence of their increasing atomic mass. Okay. While B are called as transition elements. That means the property of those elements is not just limited to one box. Although we designate into that box, it is also showing property of other boxes also. That's the reason why he used the word transition elements. So normal elements and transition elements.
I didn't understand how can like
See what I meant to say. For example, if it comes to copper, okay, copper has a properties very similar to potassium. So he arranged next to potassium. Got it? But copper also was showing the properties of magnesium. Got it? So it is volatile. Although he kept that copper just beside the potassium, it is started to show the properties of the nearby elements also. What I meant, like magnesium is ready to give away 2 electrons in water, copper is also giving away 2 electrons in water. Are you getting my point?
yeah.
Copper also exists in the form of hydroxide with copper OH twice in the form of a precipitate. Magnesium also exists in the form of precipitate MgOH twice. Got it? So that is a
Yeah.
property matching with magnesium. But where was it placed, Kapil? It was placed in the first with potassium. Got it?
Yes.
So the B subclass was put such a way that although it belongs to that group, it has that property, it is also showing a nearby elements properties also. That's why I use the word transition elements. Got it? Next, there are few boxes which were left, and those boxes he called them as Eka aluminium, which was less left just below the aluminium. Eka boron, correct? It was left just adjacent to boron. Okay, that means box A was boron, box B was left. Silicon, Eka silicon, below silicon, it was left. Eka manganese, below manganese, there was a box left. Okay, so the element which was below aluminium, at that time it was unknown. Later it was named as gallium, Ga. And Eka boron, which was in group subgroup A, and B was missing. Later, that B was found out to be scandium, Sc. Okay, Eka silicon was eventually identified as germanium, which is Ge. Eka manganese were later identified as technetium, Tc. Okay. By the way, technetium was not identified naturally at the start. It was man-made. Okay. Is this point clear, everybody? Mainly from this area, if you ask me what type of questions that will be asked, is this one. How many elements were fit? How many periods? How many groups you have? Correct? And what are Eka based elements? Got it? Next.
So just give me a
When it
second.
comes to what, Beta?
Can I just write it down?
Yeah, please write.
Yes, sir.
Right. Check. Another very important point which he emphasized was atomic weight as a factor of valency and as a multiple of valency for equivalent weight. Okay. See, there were corrections to atomic weight to the nearest integer. Okay. The nearest integers, right, which were identified based on their equivalent weight, that includes uranium,
Mm. What is
beryllium.
equivalent weight?
I'll come to that bit. Okay. Then gold and platinum. Okay. These were the corrections of atomic weight which was done based on their equivalent weight. What does that mean? See, equivalent weight is a concept where we are trying to explain the molar mass of an element with respect to a certain factor. Got it? And that factor is called as valency factor. This is called valency factor. Some books give it as n factor. See, what does this mean? Suppose if at all we have, molar mass of a substance, for example, let's say oxygen. Okay. When it comes to O2, right? Whenever you take the oxygen and try to react with H2, let's say, and it is forming H2O, is forming H2O. Got it? Now, what does this mean is that when oxygen is reacting, there is certain amount of X that will react with Y in this ratio only to form something, a mass of Z. Okay? It will use this amount of weight with this amount of weight to get this amount of Z. Correct? Now, according to the law of equivalence, which means whatever that amount, suppose if you know how to write the moles, I hope all of you know how to write the moles, correct? Moles is nothing but how much weight you have divided by its molar mass. Okay, whatever the weight of the element is, that divided by its molar mass, that will give you number of moles. Now, what I'm saying, in a chemical equation, correct, the moles might be different. That means oxygen is reacting with different moles. In fact, oxygen reacts half a mole when 1 mole of hydrogen is being used to get 1 mole of water. Clear, beta? This is how the mole ratio would be. While when it comes to something called equivalence, if this is this is having n equivalents, the same n equivalents has to react from hydrogen and same n equivalents has to form here. So equivalence is like an equal distribution of mass, total mass that is present in oxygen, and some equal distribution of hydrogen and some equal distribution of H2. Correct? And that mass, when you divide it by the given mass, let's say the given mass of oxygen is x grams, right? So that x grams divided by molecular weight of oxygen, right? And y grams divided by molecular weight of hydrogen. If you compare these two here, obviously these are number of moles, these won't be same. But for with this number of moles, if I multiply some factor, right, of oxygen and some factor of hydrogen here, then these two will become equal. And that is what we call it as equivalence. That is what we call it as equivalence. More detail about equivalence, I'm just giving you a mathematical way. More details about equivalence, how it is to be used, what is its application, we have a separate topic altogether. Got it? For now, just remember that whenever a chemical reaction is happening, the number of equivalents of the chemicals, either in the form of a reactant or the products, will always be same. Now, if that is same, what I can do, I can take this factor, divide it here. I can take this factor, divide it here. And the divided part is what we call it as the equivalent weight. And that's what we have done. See that equivalent weight multiplied by the valency factor, that will give you the atomic mass. Got it? So this valency factor and equivalent weight can be evaluated from some chemical equations. What has been noticed is that Depending upon this multiplied value, we were able to correct the actual atomic weight for which elements? For these elements, which otherwise was giving a wrong idea. That is beryllium. Beryllium atomic mass was identified as 12 originally. Okay, Mendeleev identified it as 12. Okay, but this was matching with carbon also. The same atomic mass with matching with carbon also. Then, using some chemical reactions, he was able to figure out what is its equivalent weight, then multiplied by its valency factor. Then he noticed that the atomic weight of beryllium is actually 10. Everybody understood that now? Then he corrected that, okay, this 12 is wrong, the 10 is more precise. Everyone understood?
Yes.
This way, he was able to figure out that correct atomic masses for these elements. So this was again a JE question, everybody. You better remember which elements he was able to get a correction in their atomic weights. Right, everybody?
So what is the third element?
Indium, IN, indium. Okay. Uranium, beryllium, indium, gold, platinum. Next. There are still certain elements which violate the Mendeleev's arrangement. Okay, because according to Mendeleev's, the arrangement is on the basis of increasing atomic mass. But what has been noticed when it comes to potassium and argon, argon was supposed to come before potassium because atomic number of potassium is 19, argon is 18. But when it comes to mass, this was found to be 39.1, while here it is found to be 39.9. So it's very weird that atomic number is increasing means mass number should also increase. But if you notice the mass number of 18, it is increasing so much that it is overpowering potassium. So that's why argon was never able to be placed before potassium in Mendeleev's periodic table. Okay, this was one violation. Similarly, when it comes to tellurium and iodine, tellurium was identified as 127.5, iodine was identified as 127, which is very weird because iodine, which is which is 54, 53, and this is 52, you can see the mass of this should have been lesser, correct? But it is more than iodine. That is also violating. Okay. Same goes with cobalt and nickel. Cobalt's atomic number is 27, nickel is 28. This was identified as 58.9, while this was identified as 58.6. Okay. Same goes with thallium and polonium. Okay. Clear? Where this was identified as 232, sorry, thorium. Thorium and polonium. Correct. So 232, and this was identified as 231. They were the adjacent elements, but thorium was supposed to come first. This was 90, this was 91. Correct. Clear? So these are few elements which are actually violating the Mendeleev's arrangements. Okay. I guess all of you clear with that? Please make a
Yes, sir.
note.
1 second.
Yeah.
Uh,
Yes, beta.
Sir, for every element, the atomic weight is equal to valency into
One second,
its
sorry, I'll read it.
equivalent.
This is Pa beta, protactinium.
No, sir, I have a different question. For
Yeah.
every element,
Hmm.
its atomic weight is equal to valency into equivalent weight.
Yes. Everybody done? Done? Shall we go ahead?
Yes.
Right. Now notice this one. The modern periodic table was completely derived by Moseley's. Correct? So Moseley's has used very unique phenomena. Correct? What he did, by this time it was already been learned how the X-rays are to be generated. Correct? How the different colors in an atom is forming. Correct? So all of this information was already there. Okay. So imagine, first let us understand one thing. Imagine there are few electrons in the outermost orbit and there are some electrons in the inner orbits. Okay. And let's say light is coming in the form of radiation here and it is falling on electrons. Electrons can do two things. One, first, there will be interaction of surface electrons. Surface electrons can take the energy, or they can interact with the light, take that energy and go to the higher orbit here like this. Okay. So then what happens when you send a white light, for example, some of the light is absorbed by the electron, rest of the light will come out here. Got it? Rest of the light will come out here. So this is a normal phenomena where this is called the translated, or this is the reflected rays. Correct? It is the reflected rays which will, make us to see colors. For example, if you check this Coke tin, it is appearing red color. Correct? So it is because the light is falling on it. It is absorbing, the surface electrons are absorbing some radiation. Correct? Rest of the radiations are thrown out towards us. And those radiations, after mixing together, we are seeing the intense red color. Got it? This is how usually light phenomena works. But there are cases if you send extremely high intense radiation. Okay? Suppose you are sending very high intense radiation, then instead of actually interacting with the surface electrons, the light will go and interact with the electrons inside. And they are so intense and so energetic, they will completely remove the electron out of it. Okay? They will completely remove the electron out of it, and this is not any reflected light anymore. Now what is happening? This is the electron beam itself. So that means from all the elements, if the inner electrons are coming out, right, they will come out with high energy radiations, and that converts into a form called X-rays. Okay, so that's how X-rays are generated. Okay, I'm not sure how much of you guys have experience when you go to a hospital or a clinic where you want to take out an X-ray. Typically, there will be a heater, correct, which will have a convex lens. Through that light will be passed, a radiation will be passed, and then there is some kind of a reflector, a metal reflector, and that metal usually have either a nickel or a cobalt. Okay, sometimes calcium also, but majorly it is nickel and cobalt. So the nickel surface which you have, the light with such an intense energy will penetrate all the way, and then a new light is generated. So we put it in such an angle that it will fall like this. Okay, it will go this way and then it will fall this way. And that light which is coming out of that nickel surface, that is X-ray. Everybody understood how X-rays are generated? Right. Now see this. Whenever X-rays are coming, of course, they will have certain wavelength here. So this is the wavelength associated with nickel. Like that, if I take cobalt, you will have also a wavelength of the X-ray which is associated with cobalt. What he has noticed, one very important aspect that he has noticed, is that the wavelength of X-rays decrease on moving from lighter to heavier elements. So wavelength of X-rays is decreasing. That means its energy is increasing. You know that energy and wavelength are inversely proportional. So if you go from lighter elements towards higher element, correct, then Okay, close the room. Right. Sorry. Check. If you go from lighter elements to the heavier elements, right? So what's happening here? The light is actually becoming more and more energetic. Okay, so that means if you go from nickel towards probably copper, and then if you go towards even heavier elements like rhodium or osmium or platinum and so on, in that case the X-rays would be even more intense. Got it? And that is exactly the phenomena we use with different metals to convert into a complete aura of X-rays. I mean, entire three-dimensional view of X-rays in the form of MRI. Got it? So this is a very important phenomena which he identified, and what he did, he was able to figure out how mathematically it is related. And what he noticed that the root of nu is the frequency of the radiation was directly related to the element atomic number. And higher the atomic number, more is the frequency. Of course, if the frequency is more, wavelength is less. Got it? And this A and B, he called them as Moseley's constant. And see the important pattern. When he plotted root of mu versus z, that means increasing atomic number versus increasing frequency, then he noticed that is a clearly a straight line. That means most of the elements information is falling on this line as you extrapolate. Correct? So this become a very important pattern for us to understand that as the atomic number increases, right? As the atomic number increases, the property is simultaneously increasing, the property is simultaneously changing. So now this became his main property of the elements. That is, elements can be arranged now in the increasing order of their atomic weights and not numbers, and they having similar properties repeated after regular intervals. That means after a certain while, again when you come back, those pattern would be again repeated.
So how does this show that you can put it in atomic number? I can get that.
Okay, because if the atomic number is increasing, have you noticed every time the atomic number is increasing, the frequency of the X-rays is increasing,
Yeah.
correct? Which means the property of this element is different than this element, than this element, than this element, than this element, and so on. Correct?
Yeah.
Likewise, if I take all these atomic numbers and arrange them in their increasing order, like for example, lithium, okay, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Up to this, I have arranged. Let's say I got up to this point. Got it? Up to this, I got that point.
Yeah.
Then, as you go towards chlorine, bromine, and so on here, sorry, sodium, potassium, and so on, sodium from here, sodium, magnesium, aluminium. Now, what has been observed? This pattern here, that means whatever the difference in the frequency here, that is the similar type of difference that you are noticing going ahead here. So that
Oh,
means again there is a repeated pattern. Got it?
yeah. And this won't happen if it's plotted against weights.
Yes, this won't happen if you plot it against the atomic mass.
Okay. And do we need to know the values of A and B?
No, that'll be given to you. Okay. In the question, it will be given to you.
Okay. Okay. So
Yep.
wait,
Right.
this is for all constants? Only
Pardon?
like
No,
this
this
is
was
for
constant for all the elements.
no, like in
In
the question they give the value for all constants, like even Planck's constant and all that.
no, no, in that question only it will be given separately. Okay.
Okay.
Because this is not a regular one. Correct?
Okay.
Right. Now, notice what based on this he identified there are 9 vertical columns in which we can arrange this, and he called them as 1 to 8 plus 0. 1 to 8 in a stock notation, and 0 group. And that 0 group, he called it as an inert gas group. So this becomes the total number of groups, correct? and inert gas were later introduced by Ramsay. And then there are 7 horizontal rows, which he called it as periods. That means it is pretty much derived a very similar way as that of Mendeleev's, except that in Mendeleev's, whatever the problems that were faced, especially related to the atomic masses, that has been now sorted. Clear? Because now we are arranging everything in terms of atomic numbers. Clear, everybody? Now, this was how much Mendeleev has given. Later, there were 4 scientists who finalized the periodic table, which is Bohr, Bury, Rang, and Warner. Okay, these were the Nobel laureates at that time, which finally took all the information and made it as a long form periodic table. Got it? And what they identified that there are in total 7 periods we can have, and there are 18 groups we need to have. Okay, not 8 groups are enough. We need to have 18 groups. Okay, so what they did, they categorized these groups into 2 kinds. He called them as representative elements and transition elements. Okay, okay, representative elements, right? This one, 2, then you can see 13, 14, 15, 16, 17, 18. 1, 2, and these. These were designated as representative elements. Got it? Representative means they were like the front runners of the properties of a compounds. For example, if at all I say K2SO4, okay, K2SO4 is potassium sulfate. Got it? So the entire property of the molecule depends upon how the sulfate behaves, how the potassium behaves. Is the potassium K plus? If it is K plus, that means it has more ionic character, correct? Based on the size of the potassium, its energies are defined, its lattice energy, hydration energy, its solubility, its thermal stability, all those properties are dependent. Okay, so that's why they categorize into 2 kinds. One, these elements represent the front runners of the properties of compounds. Got it? So 1, 2, and 3 to 8A. These are representative elements. And then the one which are in the middle here starts with 3B, ends at 8B first. Okay. And 8B, stock notation of 8B alone has 3 different groups, 8, 9, 10. And the 11th and 12th are designated as 1B and 2B. By the way, these numbering, this 3, 4, 5, 6, 7, 8, 1, 2 are based on the valencies of those group elements. That is, how those group elements behave. For example, if it comes to third, in the third group, we have scandium, yttrium, and lanthanum. And all these 3 elements have a high property, has a property of losing out 3 electrons, like this. That's the reason why it designated as 3B. Similarly, why 1B here? 1 has copper, silver, and gold. Commonly, all these 3 metals will give you +1 oxidation state in various compounds. Similarly, group 2B here is zinc 2 plus, cadmium 2 plus, and mercury 2 plus. That's why it is designated as 2B. Clear? So this is the first representation. 18 groups, 7 periods. Within 18 groups, 2 different ways of representations. Okay? Based on this, for exam point of view, what we need to learn? This is a table we should always be aware of. See, what is the table? First thing, we have 7 periods. 1, 2, 3, 4, 5, 6, 7. These are the 7 periods. What all shells that these periods are covering? 1s. Here it is covering 2s and 2p. Here it's covering 3s and 3p. Here it is covering 4s, 4p, and very interestingly, it will also cover 3d. then we have 5s, 5p, and then 4d. 6 would cover 6s, then 5d, sorry, 6p, 6s, 6p, then we have 5d and 4f. These are the subshells that it is covering. And then 7s, 5f, 6d, 7p. Likewise, these are the shells that it is covering. These are the subshells which it is covering. Okay. Next, how many number of electrons they usually, how many number of elements, sorry, these periods have? In the first period, there were only two elements. Okay. That includes hydrogen and helium. Got it? Got it. Next. Second period, we have 8 elements. Okay. Then lithium all the way to neon. 3 to 10. These are the elements which were observed. And next also had 8. So why 8 everybody? Because 3s can maximum have 2 electrons. 3p can have maximum 6 electrons. So the total number of elements that it can have is 8, and they both have 8. Okay. Got it? Then sodium 11 to argon 18. Next. Number of elements 18. Starting with potassium, which starts from 19 all the way to krypton, which is 36. Okay. Another 18 starting from rubidium, which is 37, all the way to xenon, which is 54. Got it? Yeah. Next, 32. Next has 32. You can notice this 2, 6p will have 6, 5d will have 10, 4f will have 14. This is the maximum number of elements that can have, and all those boxes are filled. Okay. This starts with cesium, which would be from 55, goes all the way to radon, which is 86. And last one, supposed to have 32, but all of them are not discovered yet. Correct? In fact, a lot of them are man-made. Okay, so how many so far has been found out is 26. Starting from francium, which is 87, all the way to UNB. UNB is an unknown form, which is 112. Got it? Now, if you notice these cases, what we can say, from where to where these elements are present. Okay, so if you notice that, so the first one, right, this one is the shortest, this is the shortest period. Second one is called as the short period. Third one is also a short period. Next two are long periods. Okay, and this one is the longest period, and this one is the longest continued. So usually given as star. Okay, so if the question is asked which period is the longest, answer should be sixth. Correct? If the question is asked which of the periods are shortest, answer is 1. And if the question is asked which of the following periods are short, answer is 2 or 3. Correct? I guess this part is clear, everybody.
Yes, sir.
Make a note. This should be very handy to you. Okay, you should be able to recall these things, how many elements we are placing, what are the elements starting, and what are the elements ending. Right. So this is the extended form of periodic table. Now notice something very interesting here. So check out the shade of yellow which I have used here. These two boxes together, all of these boxes together as a group, this is called as S block elements. That everything in blue here, we call them as D block elements. And everything in this orange color here, these are all P block elements. And the ones which are in gray here, these are called as F block elements. So now let's classify them in the form of blocks. All right, simple blocks. See, based on the blocks, there are 4 blocks, S block. In the case of S block, if you notice, when it comes to configuration of every element in these two, they always end up in S orbital. That's why we call it as S block elements. So the general configuration of S block includes NS1 to 2, which is the last electrons configuration. Okay. For example, if it comes to hydrogen, it is 1s1. If it comes to lithium, it is 2s1. For sodium, it is 3s1. For potassium, it is 4s1. Okay, potassium is K. And then we have rubidium, 5s1. Cesium, 6s1. This is the way it will be. While the same thing when it comes to uh, beryllium it is 2s2, magnesium it is 3s2, and so on, correct, up to radium which is 6s2, correct, not radium, barium. Okay, so this is the way you will have the configuration. That's why the general configuration of S block is ns1 to 2. Okay, since the last electron is entering into the s orbital. There are two groups here, 1a which we call it as alkali metals, 2a which we call it as alkaline earth metals. The word alkali represent that these elements become highly basic when you add it to water. Alkaline earth metal, that means they are identified as bases in earth crust. That's why they called it as alkaline earth metals. Correct? Group 1 will have francium as the last element. Group 2 has radium as the last element, and both of them are radioactive in nature. And in group 1, hydrogen towards cesium, these are the elements. In this, all of them are metals except hydrogen. While in group 2, beryllium, magnesium, all the way towards barium, all of these are metals. This is a brief synopsis that you need to know about S block. So I think it is very simple. I hope all of you got this. Yeah. Right. Now notice P block. When it comes to P block, the last electron must be entering into P orbital. Correct? The general configuration includes Ns2, Np 1 to 6. So N starts from 2 all the way goes up to 6. Okay. So that is 2s2, 2p 1 to 6, or 3s2, 3p 1 to 6, 4s2, 4p 1 to 6, and so on. This will go all the way up to n is equal to 2 to 6. So in total, there are 6 groups starting from 3a, which is the 13th group also, and 8a, which is the 18th group, also known as the zero group. Okay. We encounter a lot of metals here, non-metals here, as well as metalloids. Got it? Now, this is something that you need to learn, write and learn, everybody, starting from group 13. See, group 13. Group 13, which is also called as boron family, because the first element is starting with boron. That's why it is called as boron family. So boron, aluminium, gallium, indium, thallium, these are the elements. And the first element, boron, is a non-metal, while Rest of all are metals, right? The general configuration for this is NS2, sorry, NS2 and NP1. If it is boron, it is 2s2 2p1. If it is thallium, it is 6s2 6p1. Got it? Next goes group 14. Group 14, also known as carbon family, or since here we have a lot of crystal forms, that's why it is also called as crystalloid family. Crystalloid family. It starts with carbon, goes towards silicon, then germanium, tin and lead. Tin and lead. Okay. While carbon is completely non-metal, silicon and germanium are metalloids. These two are metalloids. And last two, tin and lead, are metals. These two are metals. Got it? Next is group 15. Group 15 is called as nitrogen family. Nitrogen family, or
और मैं इसको
more, yes beta, more commonly used as nicogens. Nicogens, because they are cancer causing elements, will usually have these element groups. So these are nicogens and starts from nitrogen, phosphorus, arsenic, antimony, bismuth. While nitrogen and phosphorus are both non-metals, arsenic and antimony are metalloids and bismuth is metal. Next is group 16. Group 16, also known as oxygen family or chalcogens, also known as chalcogens. Okay. Chalcogen is a word used when you have most of the metals, in the earth crust are in the form of either oxides or sulfides. Right? So oxygen, another word used is chalcogens. Got it? What are the elements here, everybody? Oxygen, sulfur, selenium, tellurium, and polonium. Okay. While oxygen till selenium, these are all non-metals. Okay. And tellurium and polonium, both of them are metalloids. See, metalloids are those elements which will have characteristic of both non-metal and metal. Okay. Next comes group 17. Group 17, also known as halogen family. Do not usually use the word as fluorine family, but we use it as halogens. Okay. Halogens starts with fluorine, chlorine, bromine, iodine, astatine. At is astatine. Now, all the way from fluorine towards iodine, everything is non-metal except astatine, which is metalloid. Got it? And lastly, group 18, which we call it as noble or inert gases. Okay? It starts with helium, neon, argon, krypton, xenon, and radon. All of them are non-metals. All of them are non-metals. Got it? So this is the idea we should have right from group 13 to group 18. Got it? So check out how many metalloids do we have, everybody? 1, 2, 3, 4, 5, 6, 7. Got it? So these are the 7 elements which you need to report as metalloids. How many non-metals we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and all these 6. Correct? So how many? 17. 17 non-metals we have. Everybody clear on that?
So can I write down?
Yeah, please write it down. Now look into this. What about d block elements? Okay, of course, when we use the word d block, that means you're expecting that the last electron should enter the d orbital. The general configuration includes ns1s1 to 2, n minus 1, d1 to 10, and np is 0. So there are no electrons in p here. So the last electron is actually entering into n minus 1 d orbital. Except in the case of palladium, where there are no electrons in 5s, all the electrons are found in 4d itself. Got it? Now, d orbital or d block actually have 10 groups. The starting group is 3b all the way to 8b, and then we have 1b and 2b. Okay, I told you about this already. Now, all the elements in this block are metals only, and they are usually called as transition elements, except for zinc, cadmium, and mercury. Correct? Why do we use the word transition elements? It is that they show these metals show, okay, multiple oxidation states. Oxidation state is the charge they carry when they are in the form of compounds, when they are in certain compounds. Got it? Copper sulfate, copper's oxidation state is +2. CuCl, copper's oxidation state is +1. That way, it can have different oxidation states. So when you have different oxidation state, we use the term transition elements. Got it? Another way of looking at transition element is incomplete d orbital in any of the oxidation state. That means if you identify any oxidation state and the d orbital is incomplete in that, so instead of filling 10 electrons, now we have 9 electrons or 8 electrons or 5 electrons, that means it is incomplete. Then we call them as transition elements. Got it? So now notice this one. When it comes to categorization, okay, categorized as series of elements. Categorized as series of elements. Got it? Starting from 3D 3D series, which starts from scandium, atomic number is 21, all the way to zinc, which is 30. Okay. For now, guys, for now, you need to just remember the sequence from scandium to zinc. This will be important. Scandium, followed by titanium, followed by vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Especially for 3D, you need to remember. Well, right now we don't have to worry much about 4D and 5D. So when it comes to 4D series, starting elements is lanthanum, which is, starting element is yttrium, yttrium, which is starting from 39 to cadmium, which is 48. Correct. When it comes to 5D, it starts with lanthanum, which is 57, all the way to mercury, which is 80. Correct. Now notice something very, very carefully here. See, how much is the number of electron difference here, everybody? 21 to 30, total 10. Correct. So including 21, we have total of 10 groups, right? 10 different elements. Starting from scandium to zinc, we have 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same follows for yttrium to cadmium also. So that is 39 to 48, total 10. But now there is something surprising. Here it is 57. Suddenly it has become 80. So if it was 57, correct? Adding another 9 to 8, it should become 66. Correct? Isn't it? So it should just become 66. But then how come it is going towards 18? What's happening here is after these elements, right, after lanthanum, the D electrons are not being filled. It is the F electrons that gets filled. So that means from 58 onwards, adding another 13 elements to it, correct? 58 plus 13 elements. How much we have? Up to 71. Clear? All of them we will have only, clear? Up to this we will only have F block getting filled. Only after 71, again the D block elements will start filling up. Got it? Now must be, sir, why is that happening? See, let me just go back to Aufbau's principle, everybody. Aufbau's principle. When it comes to Aufbau's principle, imagine when 6s is being filled. 6s2, right? So what is the n plus l value, everybody? N plus l value is 6 plus 0. Now the next best n plus l value when you need to get 6 is which one, right? Which one is the next best one here? The next best one would be about, because I need to get, after 6 we should get 7, right? So which one will you get here? So 6p. So that will be 7, isn't it? This will be 7. But don't you think 5d will also give you 7, right? So that will give you n plus l value as 7. Don't you think 4f will also give you 7? Yes, that is also going to give you 7. But now, when you have n plus l value same, then the lower energy will be for the lower n value. Therefore, now if I write in terms of energy, I can say 6s will have lesser energy than 4f, then 5d, then 4p, sorry, then 6p. Okay. So when it comes to S, we can fill maximum 2. And then when it comes to F, we can maximum fill 14. Then you will get into 5D, which is maximum, you can fill it as 10. And then you go towards 6. Okay. So which means after 6s2, then 4f14. Clear? Then 4f14 are been done. So notice this one. This is up to 57. Everything is be done. Now this is 4f14 onwards, 57 starts. So 57 all the way, if you add another, sorry, 14 here, so we will get this as 71. And that's when we enter into 5D. And 5D all the way up to 5D10, mercury will be done. So mercury will get as 5D10. Clear? So I guess the idea is clear, everybody. Okay. Okay. So this is about the elements, the missing elements here. The missing elements here is of 4f14. Correct? I guess this part is clear, everyone. Okay. Now notice one important aspect here. When I wrote the general configuration for D block elements, I wrote it as ns1 to 2, n minus 1, 1 to 10. But have you noticed when it comes to palladium, there is no s electron. So should I not be writing it as 0 to 2? Honestly speaking, it should have been 0 to 2. But in a generic form, because it is just an exception, in a generic form, when you write, we write it as 1 to 2. Because in some cases, definitely there is sufficient number of cases where there is only one electron in ns. And similarly, there are enough number of cases where there is both two electrons present in it. Okay. That's the reason JEE mains as well as JEE advanced accept this form more. Although in NCERT, both forms are given. As much as periodic table is concerned, put it back. As much as periodic table is concerned, they have given it as NS1 to 2, N minus 1, D 1 to 10. Okay. Now, let's get into F block elements. Right. Here, the last electron is entering into F orbital. Okay. Now, if you write the general configuration, Okay, I'm intentionally writing this that you have to practice. This is one very, very important part which has been asked in exam. That is, what is the general configuration of F block elements? See, general configuration of F block elements include n minus 2 F 1 to 14. This is 1 to 14. Then n minus 1 D 0 to 1. Very interesting. In some cases, actually D should not get an electron, but in some cases, you will still get at least one electron in D. Okay. And then comes NS2. Obviously, NP you don't have to even write it, correct? Even if you write, you just need to show it as 0. So this is the electronic configuration, general electronic configuration of F block. Okay. Let me show you some special case. When it comes to thorium, correct? Thorium atomic number is 90. So thorium is 5f0. There are no electrons in 5f. 6d1, 7s2, and 7p0. Now you might say, sir, there is no electron in F. So last electron is not entering into F. But this is an exception again. This is an exception where even though the last electron is not entering into F orbital, we still regard thorium as the F block element. Clear, everybody? Very important case. Remember that it is regarded as F block even though the electron does not enter into 5F. Okay. Okay. Then all elements here, all elements are placed within third group only. It enter within the third group only. What does this mean? Let me take you back to the periodic table once. Check it out. When it comes to periodic table, notice carefully. This is the third, group, right? In the third group, if I ask you how many elements are there in this box, answer is not one. There is not just one element in this box. Within this box, we have total 15 elements, including lanthanum. Okay. First element is lanthanum. Then cerium onwards, the filling of F block starts. So all the way from cerium towards lutetium, that is 71. Up to this, you will always have F block completely filled. Okay. Sorry. Check. Sorry, guys. Check. So, like I said, in the third group, not just lanthanum, all these elements are present in it. Similarly, in the third group, when it comes to seventh column, that is seventh period, that also has all these elements. Correct? Now, very interesting question. Look into it. If I ask you, which of the following groups in periodic table has the maximum number of elements? Answer is third period. Got it? This has 15, this has 15, so 30 plus 1 plus 1. So how many elements, everybody? 32. So let me write down that as a note. Got it? Note here is third period has a maximum of 32 elements present. Yes, beta, you're saying something? Someone was saying something, Dave? Someone? No.
Oh, sir.
Okay. Right. Okay, beta. Check. So, very important thing. Please remember that point. Correct? Next. Here, we have two series is present. Correct? In this case, we have two series. Just like how we have three different series in D block, here we have two series of elements. Two series of elements. Got it? The first series is called as lanthanoid series. Lanthanoid series. Okay. It starts from lanthanum. Element is 57. Correct? And goes towards cerium, which is 58. And from cerium all the way, it runs up to lutetium, which is 71. And similarly, we have actinoid series. Actinoid series, which starts from actinium, right? And the next element is thorium, which is 90, goes all the way to Lr, which is lawrencium. Correct? These are lawrencium cases. Please check. This is lanthanum and actinoid series. Lanthanide series and actinoid series. Okay. Now, both these lanthanides or actinides are very, very rarely found. That's why they are called as rare earth metals. These are called as rare earth metals. And all actinoids are radioactive elements except few lanthanoids, correct? And elements after uranium, uranium is 92, these are called as transuranium elements. In fact, all of them are man-made. Clear? Uranium is naturally occurring, but thereafter it will be mostly man-made. And these are called as transuranium elements. Okay. Right, everybody? Okay. So please look into that quickly. This is about F block elements.